Hello, welcome to another Further Maths tutorial video on vectors, where today we're looking at another method for finding the shortest distance between two lines, this time using the cross product. Due to a quirk between the different examples for A-levels, the cross product is not a technique that's officially on all of the exams where you might be required to find the shortest distance between two lines. However, despite this, you are always allowed to use this method, even though it's not the first one the examiners might be expecting you to do. And with that said, I therefore would actually recommend you do use this method despite that fact, because of the fact that although it's the one that's conceptually, from a geometrical point of view, the hardest one to get your head around from a understanding why it works point of view, but from an actual calculations carrying it out sort of point of view, it is the quickest one to do, the easiest one to do. So that is why I'd recommend using this method to do this sort of problem. With those important notices out the way, I thought we'd start by looking at a demonstration to help us understand what's going on with this stuff from a geometrical perspective before we actually launch into doing the calculations aspect of this stuff. As you can see, I've got two rulers, which we're going to use to represent our two lines in 3D space. These two lines are skew, which means, as you can see, they're not intersecting, but also you can see, as we're looking from above now, that they aren't parallel either. However, there is one particular angle we can look at these lines from where they look slightly parallel to each other. They aren't officially parallel because we've got depth perception, so therefore we can see that one of the lines as we travel from right to left is going away from us, whereas the other line as we go from right to left is traveling towards us. So they aren't officially fully parallel, but if we take this as a 2D image, the lines look like they're traveling parallel to each other. This is important because the shortest distance between the two lines is only happening in one place, as I'm indicating here. However, it's a bit of a pain to find exactly where that shortest distance is taking place. So instead, we're going to make use of a particular trick. Although the distance between the two lines does start to change as we move along the lines, we can see the height in between the two lines is staying the same because of this fact that the lines look like they're sort of parallel to each other. Although this seems rather convenient because it looks like I've just arranged these two lines in this way so this happens, there always will be an angle you can look at your two skew lines from in 3D space where this sort of effect is occurring. So therefore that means we can end up picking any 2 points we like on these two lines, and then we can use that to form a triangle. And then interestingly, as is the case for the height on my triangle that I've got here, the height of this triangle is always going to be identical to the vector where the shortest distance is taking place. So it's weird because this triangle has parts of itself floating in the air almost, but at the same time, one of the lengths of the sides of this triangle is identical to that shortest distance. And therefore, we can take advantage of this to help us calculate what that shortest distance is, because we can choose where we form this triangle while still also knowing that one side of the triangle is that length that we're trying to find. Cool, so that's what we're trying to do. Now let's actually do some calculations. So I've got an example. We've got to find the shortest distance between the lines with these two vector equations. I'm just going to launch straight into doing this as an example rather than explaining the steps beforehand, just because it's one of those methods where it's easier to see it by doing it rather than to explain it in words beforehand. And also, now that I know what the question's asking me to do, I'm going to get rid of those words so I've got more room to work with. A good thing to do to begin with is to draw two lines. Drawing a diagram is always a big help with vectors, as I've mentioned in previous videos, so no difference here. I've drawn two lines to represent our two lines we're trying to find the shortest distance between, and just like in my demonstration, it's worth pointing out these lines are skew, not parallel, but when you look at them from a certain angle, they look like they're parallel, so that's what I'm drawing. And then the first thing I want us to do to actually start solving it is I'd like us to identify any 2 points on the two lines. So 1 point on each line is what I mean there. So therefore it makes sense to pick the easy option and just pick the 2 points that the equations of the lines themselves give to you. So therefore this point could be minus 1963, And then another point on the other line would be the point -8, 10, 16. Now, unless you're super lucky, these 2 points won't be in the position of where the shortest distance is. So therefore, that's why I've drawn them sort of looking diagonally from each other. What I'm then going to do is find the vector joining those 2 points together. And to reduce the number of minus signs I'm having to deal with, I'm going to do it as -8, 10, 16 minus -19, 6, 3. Now, of course, technically, if you subtract vectors the other way around, it changes the direction of the vector, which in theory does affect the problem, but in reality, because of the way I'm doing the approach I'm showing here today, that means that in the long run, it won't matter what direction this particular vector is going in. Cool! The next thing we're going to do is we're going to form the triangle I showed in the demonstration. And the way I'm going to do that is, of course, making use of the fact that we want a right-angled triangle. So we want the side over here involved in the triangle to be at a right angle to both this line, but I also want it to be perpendicular to this line. And that's interesting because if only there was a special trick we could use to instantly find a vector that's perpendicular to 2 other things. Oh yes, the cross product. So therefore we're going to use the cross product of the 2 direction vectors of our 2 lines to find basically the direction of this second side of the triangle that I've drawn. And it is worth highlighting that this is just going to be the direction of this side of the triangle. It's not going to be an actual vector joining 2 points, so it can't be used to find a length of actual distance that you can see on the diagram. And that's because I'm calculating it using 2 direction vectors. And the 2 direction vectors are only meant to be used to indicate the direction of things, not anything to really do with actual proper lengths of things. So therefore, I'm doing 10 minus 2, 0, cross-producted with -11, -2, -6. And the method I like to use for that, as I've said in previous videos, is to use the determinant method. So therefore, writing that out, we will get, of course, the first bit would be the I component, and it would be -2 times by -6, which is positive 12, minus 0 times by -2, which is 0. Because it's the j component, we put a minus with some brackets. Then we do 10 times by -6, which is -60, 0 times by -11, which is 0. And then the k component, we have -20 minus -2 times by -11 is positive 22. Cool. And if you simplify that down, you will get positive 12, positive 60, and -42. Cool. Now at this stage, as I already mentioned, this is only a direction vector, and that's important to note because some people might be tempted to just find the magnitude of this vector and go, oh, that's the shortest distance, but it isn't, because it's just indicating the direction that the shortest distance will be going in. What we really want to do in actual fact is use the triangle to find the shortest distance. And we're basically going to be doing some trigonometry, and of course an important part of that would be to have an angle involved. So what we're now going to do is we're going to try and find the angle that's here, that I'm going to call theta. We know theta must be an acute angle because it's inside a right angle triangle. But how am I going to find theta? Well, good news is I've got the directions of the vectors either side of theta, so therefore I can use those to find theta. So 11, 4, 13 and 12, 60 minus 42, the 2 new vectors I've found, I'm going to use with the dot product to find what theta is. So giving ourselves more room now, let's have a go at doing that. So cos of the angle between the 2 lines. Now weirdly, I have just called it theta, so you might be wondering why I haven't called it theta. We'll come to that in a bit, but for the moment I'm just going to say it's the angle between the 2 lines, and that will equal the dot product between 11, 4, 13 and 12, 60 minus 42 divided by the magnitude of 11, 4, 13 times by the magnitude of 12, 60 minus 42. Cool, let's get going. So 12 times 11 would be 132, plus 4 times 60, which is 240. 13 times by minus 42, that would be 420 plus 126, so that is 546, but it's a minus. And then the magnitude will be 11 squared plus 4 squared plus 13 squared. Obviously, it makes sense to make good use of calculators in this stuff. And then the magnitude of the other thing is 12 squared plus 60 squared plus 42 squared. Extending our lines onto the notation is correct. Individually simplifying the three parts that are written there, the top will just become minus 174. And then individually simplifying the two square roots, we will get 3 root 34 according to the calculator and 18 root 17. Now that is a conscious choice to only individually simplify the two square roots on the bottom rather than typing this in the calculator as one big fraction and getting it to simplify immediately as one big thing. And the reason for that you'll also see later, but just to make the point that I'm doing this on purpose, because you are technically wasting your time if you try and simplify it all together because of what we're going to be doing later. Cool. Now I can talk about the next thing, which is, as I said, we want to find the angle. Now you've got a couple of choices here. You could either do arc cos of the thing we've found here and find what the angle is. And then, of course, realize that we wanted an acute angle. So if you do arc cos of your number and it ends up not being an acute angle, you could then, of course, do 180 minus the arc cos value, whatever it was, to make sure it then is an acute angle. Because, of course, whenever you find the angle between two lines, there's always an acute one and an obtuse one. So if you've accidentally found the obtuse one, it's just basic angle problem solving to find the one you want. However, you don't need to go to all that effort because there is a nice little trick that you can use that speeds this process up. Did you know that if you want to find the cosine of an acute angle, all you've got to do is take the modulus of the cosine of an obtuse angle? So therefore, that's really neat because it means without even doing arc cos of the fraction that I've calculated here, I can already tell I've accidentally found the obtuse angle rather than the acute angle because of the fact this fraction has a negative value. And therefore all I need to do to make it cosine of the acute angle that I want, instead of having to find the actual angle, I've just got to take the modulus of this fraction, which in other words just means get rid of any minus signs you see. So therefore the cosine of theta is just going to equal positive 174 over 3 root 34, 18 root 17. Again, still keeping those square roots as separate things for the moment. If you're wondering why this trick I've just shown you actually works, why we're allowed to do it, I do actually already have a video proving this fact because I hate just quoting things without explaining where they come from. So do take a look at that video if you do want to understand why that little magic trick there works. But anyway, now that we've found theta, or rather now that we've found cos of theta, finding the shortest distance is going to be really easy. Because if I want to find the shortest distance between the two lines, it's going to just be, if we reference back to our triangle, the hypotenuse of the triangle times by the cosine of the angle. That's why I don't actually ever need to find the angle itself, and just finding cos of the angle is enough, because hypotenuse times cos of the angle will find the length of the adjacent, which is exactly what we want. It's worth noting, just like on my demonstration, this side of the triangle is the side of the triangle that was floating in space, and that's why we never ended up doing anything with that side of the triangle, because we couldn't, because partly this diagram is fooling you into thinking it's part of the line that we've got down there. So we really do just need the hypotenuse and the angle, and that's enough. And then I can now explain why I didn't simplify the square roots, because if we're doing the length of the hypotenuse would just be the magnitude of the vector 11, 4, 13. However, as part of doing the dot product, I already found the magnitude of 11, 4, 13. As part of that process, it ended up as part of the denominator for the fraction of cosine of theta. And so therefore, instead of having to actually calculate 11, 4, 13 as a magnitude, I just realized I've already calculated it earlier. It's appearing on the bottom, so if I'm now re-multiplying by it, it's just going to cancel it out again. So therefore, the only things I'm going to be left with are the parts of cos theta that weren't from the magnitude of 11, 4, 13. So therefore, that will just be the 174 on the top and the 18 root 17 on the bottom. So I didn't even need to do any actual calculations there to do the magnitude times cos theta. I'm just cancelling stuff out. But now I can choose to type all this stuff into the calculator to then get it to fully simplify this fraction. And if you do that, you'll end up with a final answer of 29 root 17 over 51 in exact form. So there you go. We have found the shortest distance, and those are the steps you need to do. However, as usual, to make sure my videos are as comprehensive as they need to be, I would be doing you a disservice if I didn't actually point out that there was another approach using the cross product that can help you find the shortest distance between two skew lines. And it is, if you've got the two lines in this format, just like we did in our example, then you can simply use this formula to find the shortest distance between L1 and L2. So there you go. If you are somebody who loves using formulas, then you're welcome to use that. However, things to bear in mind, first of all, this formula is not in the form booklet, and therefore as a result, personally, if you're asking my advice, I would advise that you don't use this formula. I wouldn't recommend it if I was doing this stuff myself, and that's for a number of reasons. First of all, because it's not in the form booklet, you're going to have to make the effort of remembering off by heart. The problem with that is although the formula is itself relatively simple, it's actually quite difficult to remember and easy to get wrong, because there's 4 different vectors involved, A, B, C, and D, and there's loads of different operations in various different places. We've got a minus, we've got a dot product, we've got a cross product, we've got a fraction, so division, and then we've got 2 different modulus signs happening in 2 different places, having 2 different roles. So the problem is there's a lot to get wrong there, and the problem is therefore you make one mistake, therefore you've mucked up the entire thing. So therefore that's why personally I'd still do the approach we were doing before that I showed in the example we just did, because also secretly if you're doing that approach, you are just doing the same steps this formula is showing, but you're at least understanding why you're doing each of these steps, which makes it easier to remember rather than just a mindless bunch of steps told to you by a formula. So there we go. That is my take on it. Personally, I wouldn't use this formula, but it is doing the same thing as what we did before, but just written down as one big thing rather than making you think about the individual steps. So there you go. That is ultimately consistent with what I've said in other vectors videos as well. I'm very much an advocate of drawing diagrams and problem solving your way there geometrically to get what you want, rather than just mindlessly remembering 50 billion formulas, because that ultimately makes the vectors chapter for a lot of students seem way more scary than it needs to be, versus just being able to see what you want and what you need to calculate it. But anyway, there you go. That's how you find the shortest distance between 2 lines using cross product. It's worth mentioning no matter which exam board you are doing, they all allow you to use this when finding the shortest distance between 2 vector lines, even if this method is technically not part of the module for all of the exam boards. It's an allowable technique that does appear in the mark schemes. So that will do us for today. I'll see you in a future video. Goodbye!